Welcome. In this video, we are going to review the nice DDIM paper from great researchers from Stanford University. So what do? They introduce a new class of diffusion models that is the generalization of DDPM, but that is 10 to 50 times faster to sample from. And while it is faster to sample from, it has the same training objective as DDPM. So what does that mean? That means that you can reuse a model that has been trained with the DDPM objective, for example, Stable Diffusion 1, Stable Diffusion 2, SDXL. You can reuse a model that has been trained with the DDPM objective, but you can, let's say, warp it into this new class of diffusion model and sample from it 10 to 50 times faster. Okay. So, for example, if you are using the diffuser library, you will see that when you sample from a model, you have all the DDIM parameter because you sample from DDIM or not from DDPM. DDPM is just too slow. Okay, so basically, here they discuss a bit GANs versus diffusion models. While now people don't talk much about GANs, everyone is talking about diffusion models. GAN are still very useful in the industry because they're very fast to sample from, while DDPM or diffusion models are slow. To sample from a DDPM, you need to query the neural network thousands of times. Even though DDIM makes that faster, it's still slow. GANs are still great in terms of speed, but diffusion models are much simpler to train, much simpler to scale, and usually produce higher quality samples. Okay. So basically, as we've said, they show that the training objective of the new model is exactly the same of DDPM. On it has the great implication that we've mentioned, so that you can reuse models that have been trained with DDPM, but the model is a shorter, let's say, generative chain, and therefore you can sample from it in a smaller number of steps, but we are going to discuss that later. So the three benefits of the paper is that DDIMs are faster to sample from. They have what we call this consistency property, which means that the same initial latent variable will produce results that have similar high-level features. And because of this, that means that if you sample 10 images with the same initial latent, you will have 10 similar-looking images. But that also means that you can use that property to do latent space interpolation. You can interpolate between images in latent space. That's something that has been done with all generative models. But here, basically, in the past with DDPM, you could not do that because of the stochasticity in the generative process. Two images with the exact same initial latent would produce very different results. But DDIM allows to have consistency and to interpolate in latent space. So okay, that's a bit of the high-level overview. Now let's dive into the math. Let's dive into the explanation on why it works. As we know, DDPM, I have a few videos about diffusion models, about DDPMs, a few implementations from scratch. So I will not go into the background. I assume that you already know that. If not, please have a look at my other videos. But basically, we have DDPMs, which are latent variable models trained with the ELBO, with the variational lower bound objective. That is rewritten here. As opposed to autoencoders, for example, where we learn at the same time the encoding and the decoding. For DDPMs, the encoding is fixed, so the thought process is fixed. And usually the latent variables are high dimensional as opposed to other models such as autoencoders. So basically with DDPMs, we sample from x0, so our data. We sample a Markov chain, so we sample latent variables by adding noise, little by little, we add noise to the clean data, and we do that recursively. A special property of the thought process is that to sample from xt, so let's say you have so big T, it's the number of time steps. Let's say you have 1000, that's the default value that is used in most papers. You have 1000 steps. let's say, for example, that you want to sample from small t equal 500. You don't need to simulate the full 500 first steps. You can directly sample from q of t. So you can directly sample x 500 given the initial clean data because of some properties of Gaussian distributions. So that's a very nice property. You will see it in all codes. When you train your DDPM, when you sample, let's say, x500, you will not simulate the full fold process. You can just directly sample from it. So basically, we have this marginal distribution, q of xt given x0, and we can directly sample from it. And that will be important later. Okay, so because of that, we can, using the reparameterization trick, we can directly sample from xt from x0. This is discussed in the DDPM paper, but basically that's a training objective. And basically there is a parameter gamma. So basically gamma is some kind of weight. So for each time step t, you can weight the training objective. Okay, so some for some papers, they make good use of this weighting parameter. Maybe I will not discuss about that now, but basically for most of the papers, or for the initial papers on DDPM, gamma t is fixed to 1 for all t. So we call that L1, the L1 objective. Okay, so usually, so why DDPM is slow? It's because usually t is high, let's say 1000. And why do we choose t equal to 1000? Why not, for example, just 10, so that it will be just faster to sample? It's because we make some assumption about the reverse process. So we have the forward process where we add noise to each time step, and then we have the reverse process. We train a neural network to reverse this process. What we do, we make the assumption that the reverse process is Gaussian. And for it to be Gaussian, we need that the delta t, so the difference between two time steps, we need it to be small, and that's why we use a lot of time steps. So basically, yeah, this is said here in other words. Yeah, but okay, basically you make the assumption, you make some assumptions, and for it to be true, you need the time steps between two successive, well, you want the delta between two successive time steps to be small. So the key observation from this paper, or the main takeaway, is that as we've discussed, in DDPM, the DDPM objective only depends, so L gamma or L1 only depends on the marginal, so q of xt given x0, but it does not imply the joint distribution. So it does not care about the latent variable that went from x0, well, or let's say x1 to xt minus 1. We don't care about those intermediate variables, we just care about this marginal. But we do not care about the joint distribution q of x1 to t given x0. And the thing is, there are many joint distributions that can lead to the same marginal distribution. So basically here what they are going to do in this paper is to have a look, or to study in more details, the joint distribution. Well, or basically focus on one joint distribution in particular. So basically, yeah, they introduce a new family of inference distribution. So q sigma of x1 to t given x0. So basically that's the joint. Okay, so basically they write it like this. That's different than the DDPM objective. So here you see that xt minus 1 depends on xt on x0. So that's a non-Markovian process. But previously, what we did, so for DDPM, we assume that xt minus 1 only depends on xt. So we assume that it was a Markovian process. Here we make the assumption that it's no longer the case. Xt minus 1 depends on xt and x0. So it's non-Markovian. So basically, yeah, but basically in the DDPM paper, the authors postulated this distribution family. Now in the DDIM paper, they postulate that distribution. Okay, so in green, this is what we need to these are our constraints. Let's put it that way. So these are the marginal that we've discussed. We want the marginal to have this this form, right? On here, that's exactly the same marginal, but where t is equal to big T. Yeah, we've said, okay, we are constrained by the marginal, but not by the joint. So basically, these are our constraints. And basically, then they define the joint of the distribution family they've introduced. So Q sigma of xt minus 1 given xt on x0. This is the new, this is the joint. And this is the form it has. And how do they find the mean on the standard deviation of this distribution? It's because we have those constraints in green. And because of those constraints, it fixes the mean on the standard deviation of this distribution. And this is, there is a proof in the appendix, if you want to have a look at appendix B, Lima 1, okay? So that's the reverse process, okay? We go from xt to xt minus 1, but this is a condition on x0 as well. And we can also find the equation of the fourth process using Bayes rules. Okay, so yeah, okay, so again, we are no longer Markovian. So now xt does not depend just on xt minus 1, it also depends on x0. The issue is that we don't have x0 when we sample, right? What we want to do, I'm just making sure. Yeah, okay. So what we want to do when we sample, we start from x of big T, x1000, right? And we want to go from x1000 to x0. So we want to go at each time step, we want to go from xt minus 1, from xt to xt minus 1. But here to go from, here to find xt given xt minus 1, we also need x0, but x0 is where we want to go. So we don't know x0. But basically what we can do, we can go to equation 4. And here we have some relation. So basically that's from the marginal, right? That's constrained from the marginal, q of xt given x0. So basically there is a relation between xt and x0. So basically if we have xt, if we know xt, we can predict x0. So basically here we get, we can estimate x0 given xt. Okay, we've just returned the equation. Okay, so basically when we write that, then we have this, we have our generative process with the distribution, or we sample xt minus 1 given xt, where we approximate x0 in this, so this, well, this is the approximation of x0. So basically that's the equation we've just derived, that is non-Markovian. With diffusion models, you always have issues. You always have boundary conditions at t equals 0 or t equals 1. It depends where you start indexing. So basically here there is this boundary condition. Let's ignore that for now. And basically, if I sum up what we've done, if we step back a bit, the only thing we've done, we have introduced a new distribution family that is non-Markovian instead of one that is Markovian. So instead of introducing this distribution family, now we've introduced a new one, which is this one, okay? And basically, when we work with this distribution, we do a bit of development. We arrive to this training objective that if you compare it to the L gamma objective that we've seen before for training DDPM, is very different. And also here you see that the objective depends on sigma. So on the so your fault process is characterized by the standard deviation sigma. So basically here your training objective depends on sigma. So it will seem that for every sigma you choose, you will need to retrain a new model. So that's one thing. And the other thing also is that this objective is different from L gamma. But there is this theorem. So basically for all sigma that is greater than 0, there exists gamma. So gamma is a set of weights, okay? So you have, if we go back to the L gamma objective, you know, each time step objective, well, you have the sum of different terms, and we have one term for each time step. So basically each term for each time step is weighted by gamma. So gamma is the set of weights for each time step. So basically here this theorem says that for all sigma greater than 0, there exists one set of weights on a constant such that G sigma is equal to L of gamma. And basically that means, well, there will be some implication about this theorem, but first we know that okay, if the parameters theta of the model that predicts the noise is not shared across all time step, so basically that's why diffusion model are conditioned on the time step. They at each time step we do some noise prediction, but this is always let's say that a different model, even though the weights are shared. That the model is behaving differently for each time step because it's conditioned on t. But basically here with this property, okay, maybe I can state it, but you can read it later. But basically, yeah, if the parameters are not shared across different time step t, then the optimal solution will not depend on the weights gamma. Okay, so basically that depends that means that if you ensure that, then you can choose any weights gamma and you will have the same global optimum. And that's why in DDPM they just choose L1. They just put 1 to every time step because it leads to the same global optimum. So that's one takeaway. So basically that means that here you have L gamma, but you could just use L1 because for all the gamma have the same global optimum. So basically that means that you have G of sigma is equal to L1 plus C. So basically that means that for all sigma, whatever the sigma is, you have the same global optimum. Well, G gamma is equal to L1 plus a constant, but we don't care about the constant. So basically what does that mean? That means that you can train the model, the DDIM model that we've just introduced with the DDPM objective. Okay, great. So we've already explained how to sample from the model. So basically at each time step, you predict x0 and then you plug that into your equation. So basically once you have, basically that's all you sample, xt minus 1 given xt on x0, where x0 is predicted. So basically that's the distribution you use to sample. So basically by just using the reparameterization trick, that's all you sample from xt minus 1, okay? Where x0, you don't have it, you predict it from rewriting equation 4, okay? So basically here you see that there is one term, sigma, and basically you can play with the sigma. We've said that for all, whatever sigma is, the training objective is the same. So that means that once you've trained a model, during inference, you can use any sigma you want. And basically there are two specific cases. When sigma t is equal to this for all time step, then you go back to DDPM. As we've said, DDIM, well, this class of generative model that they've introduced is a generalization of DDPM. So basically if they use that, we are back to DDPM. But if we say sigma is equal to 0 for all time step, then that becomes a deterministic model, except for the first time step. Again, there is this boundary condition. Let's not discuss about that for now. But otherwise, if you start from x1, then the reverse process is, well, both the forward and the reverse process are deterministic. And then we call that DDIM. That's an implicit diffusion model. Well, implicit probabilistic model. And that's what we call DDIM. So DDIM is just when sigma is equal to 0. But otherwise, yeah, I'm not sure they put a name on the general model they introduce. So okay. So last thing. So for now, what we've done, we've introduced this new model, let's say DDIM. But for now, we've assumed, okay, we've with T steps for the forward process. And then the generative process, the reverse process, is forced to have T steps. However, again, the L1 objective, it only depends on the marginal, so Q of xt even x0. So we don't care about the intermediate time steps. We only care about the marginal. So that means that we can, for example, instead of, for DDYM, instead of having 1000 time steps, we can just define new time steps, for example, tau. And for example, tau, we have only 50 time steps instead of 1000. So basically, for example, you just take one time steps every 20 steps, but you make sure that it has the same marginal. So Q of X, basically what you care is the marginal. So if this is the correct marginal, that's fine. So basically what you can do, you can train your DDPM with 1000 time step, and then during inference, use DDIM with only, for example, 50 time step. And we've seen that basically if we want to train this model, this DDIM model, it has the same training objective as the DDPM. So basically you can train with 1000 time step and then do inference with 50. Okay, that's what they say here. We can train a model with an arbitrary number of forward steps, but only sample from them with fewer time steps. Okay, I will not go through the experiment. I think you can go through them at your own pace. For example, they compare DDIM to just DDPM. So let's say you train DDPM with 1000 time step, and then you do inference with, let's say, 50 time step. Basically, it does not work. You get very bad sample, but DDIM allow to do it with good mathematical foundation and with good results. Okay, so I think that's all for this paper review. I hope that was helpful. Yeah, thank you. Next week I will make a video where I implement DDIM from scratch using PyTorch as always. So subscribe if you're interested and if you want to see the implementation.